Next, we're going to take a look at section 8.2, which is integration by parts. And integration by parts beckons us back to something that you guys keep wanting to simplify, and I keep telling you we can't do that because you can't simply take an antiderivative of two different pieces of a product and then put them back together and say that was the antiderivative. So we have to think about the product rule, and this is where this is coming from. So do you remember the product rule for a function? And we're going to deal with the function u times v. So if you had the function u times v, and u and v were both, something with x in it, they both have components of x in it, what would you do to find the derivative of u times v? What's the product rule? So tell me, who was going to, Caesar, did you have it?
Well, first time, derivative first.
Okay, you can do it that way?
Yeah, I did it that way, yeah.
That's okay. And then what?
The second one known and plus first times the derivative v.
Okay, so this is one variation of that product rule. Do you guys remember that? Okay, good. So here's the problem with that. The problem with that is that we tend to think when we're working with the product rule, we're starting on the left and we're moving to the right, but that's in terms of being able to take a derivative. We want to do something that allows us to take an antiderivative, right? All right, so imagine now that we take what's written here and we integrate this. So if we integrate this, we'd integrate all three pieces. It's a property of integrals. And on the left-hand side, that would result in u times v, right? You take the integral of a derivative, you get the original function uv. So that's fine. But on the right-hand side, there's not a way to simplify those very well. So what we're going to see them written as is the integral of v, and then the u prime is the derivative of u, so that's du. And then over here, the integral has u in it, and then it has the derivative of v, which is dv. So this is the notation that you'll see used for this. And if we rewrite this, that is, we move some pieces around, we end up with theorem 8.1, which is the first theorem in this section in your book, which is integration by parts. So I'm going to flip to the next screen so I can show you what I'm referring to. When we have u and v functions of x, and if we write this, we can have the integral of u dv equals u times v minus the integral of v du. So you guys have them on the same sheet of paper, one right after the other. What did we do?
Just subtracted.
Right. We just subtracted which piece? The v du piece, this one right here. We just subtracted this to the other side, right? That's all it is. So that's where integration by parts comes from. It just comes from what we mean by the product rule. But what it allows us to do is it allows us to take something that looks like a product and find its antiderivative. But there's a process involved in doing that. Because as you can see, there's lots of pieces, and somehow we didn't deal with lots of pieces before. So let's take a look at how we deal with this. Some guidelines for choosing. As we're doing this, this is going to feel somewhat like use substitution. We're going to have to make a choice about what these pieces are going to be. So we're going to have to decide what we're going to let the v, the u, and the dv become. So these are some guidelines. They don't always work. They're guidelines. They're not rules. That's different, right? So these are guidelines. My husband and I were talking about we were talking about sin in the church, and there's this discrepancy in our small group stuff that happened on a Wednesday night about smoking and drinking. And there are these guidelines that church set up, but they're not rules. That is, the Bible does not say do not smoke, right? But it's a good guideline. Would you agree? Probably not a good idea. So these are guidelines in that same sense. They don't always work. It's not a for sure thing that's always going to happen. There's no rule, but it is a guideline. So the first one is to let dv be the most complicated part that fits the integrand of a basic derivative or a basic integration rule. You'll see us actually do some of these, and I'll tell you which piece we're sort of using as a guideline when we make the decision. U we often let be something that will be simpler when we take a derivative. So you see polynomials do this, right? So when you take a derivative of x to the fifth, it becomes 5x to the fourth. The degree goes down. It gets simpler, right? But there are some things that don't do that. For instance, when I take the derivative of sine, what happens? It becomes cosine. Is cosine any simpler than sine? No, it's almost identical, in fact, right? I mean, it doesn't really change much. Same thing when you're dealing with like exponentials, e to the x. What's the derivative of e to the x? E to the x. Did it get any simpler? No, it didn't get any simpler. So often u is not helpful to be those things. That doesn't mean it can't be. It's just not the piece that gets any simpler in those cases. All right, so we're going to take an example. We've got x cubed natural log of x. And as we're doing this, I'm going to set up sort of a pattern of how I think about it. You don't have to do it this way, and not everybody does, and that's okay, but it helps me, because I'm a visual person, to have a pattern of how to put things in. So the way I set up my u substitution, or my integration by parts, is that I put a u over here, and then a du, and a v, and a dv. Because you need all four of those pieces in order to do this problem. So somewhere on there, you're going to have to identify what you've let things be. But what you have to do is you have to fill in along this diagonal with what's already in the problem. So the pieces that are in the problem have to go in the u slot or in the dv slot. There are no other choices. So this is a rule. Okay, this is not a guideline. You have to fill in those pieces. And everything, in fact, I should have made this all the way across, everything here has to be present in either the u piece or in the dv piece. Has to. Because what we're going to do is we're going to do some substitution back in. It's not u substitution, but it's integration by part substitution. Okay? All right, so here's what we're going to take a look at. We have two pieces of this function. We have an x cubed, and we have a natural log of x. Which piece actually gets simpler when we take the derivative? X cubed does, but natural log of x has a problem. You see, if I put the x cubed right here in the u spot, then that means that the natural log of x goes down here. What's wrong with that? Yeah, and so I haven't actually said that's what we're about to do, but Parker's exactly right. This piece right here, if I were to put, and I'm going to erase this in a minute, so don't write this down. If I were to put the natural log of x in here, my next step is that I'm going to have to go up here and I'm going to have to find its antiderivative. Because if dv is a derivative, natural log of x, v is an antiderivative. And what's wrong with finding the antiderivative of natural log x? It's not one of the rules we've got. We're about to figure out how to do it in this section, but it is not one of our basic antiderivative rules, is it? So here's our first place where those guidelines don't seem to really help us, right? Our guidelines would have said, well, x cubed would be a great thing to put in for u, but we can't here because the other piece that's in the problem doesn't work in the v spot, the dv spot. All right, so let's actually figure out where we're going to put some things here. We actually have to put the natural log of x in the u spot. And anytime you deal with the natural log of x in the problem, it's going to happen. Okay? So if you've got a natural log of x in your problem, it's going to go in the spot where the du is, where the u is, sorry. Okay, sorry, I want that to go away. All right. So that means that the other piece is, and there's two other pieces, actually have to go in where the dv is. One of those is the x cubed. What else has to go down here? The dx, because it needs to be somewhere, has to be somewhere. Well, it has to be there because that's the piece that's actually a derivative piece. All right, so we're going to now take a derivative and an antiderivative. This is why I told you we're going to be working with both of these at the same time for the rest of the semester now. So what is the derivative of natural log x? 1 over x dx. Yes, thank you. What is the antiderivative of x cubed? Good. 1/4 x to the fourth. And then the dx is removed because I'm taking an antiderivative. What we're really doing, without writing it each time, is we're doing this to go back up a step, right? We're taking the antiderivative of both sides. The antiderivative of dv is v. The antiderivative of x cubed dx is 1/4 x to the 4th. Okay? This is the piece that has to be filled in before you can continue the process. Now what we can do is we can actually use this theorem over here, theorem 8.1. So I've identified u and I've identified dv. That's what I had to do. By this now, what it says is I should multiply u and v together, and then I should subtract an integral of v du. So let's see that happen. The first thing I'm going to do, so this says I should do uv minus the integral of v du. So u times v is the top line of the information that I've written down here. It's the natural log of x piece, and it's the 1/4 x to the 4th piece. You can write it in whatever version or form you like. I'll just keep it as I've got it in that order to alleviate any concerns, although I'm going to probably change it in a little bit. This is u times v. Right? No problems. It's not showing up yet. Well, let's just give it a sec. Here we go. Now do we agree? That looks like u times v? Excellent. All right, and then we're going to have a subtraction sign, and we're going to do an integral. So here's where this visualization thing to me is what I think of. When I work with integration by parts, I know I put things in along the top to bottom diagonal. Okay? And then the first thing I do is I multiply across the top, and then I subtract the other diagonal. That's the visualization that I think about every time I do integration by parts, because I'm a visual person. And I know not all of you are. My daughter's not at all a visual person. But this really does work well if you are. All right, so the other diagonal has the v, which is the 1/4 x to the 4th, times du, which is 1/x dx. And while that looks like it's still a product over here, it's a product we can simplify with algebra, isn't it? Okay, so this is, I'm going to put the 1/4 x to the 4th in front and then natural log of x, because I don't want it to look like that anything is actually multiplied by the x that's underneath the natural log or inside of the natural log. Over here, I can write my 1/4 in front, because I kind of like to do that. How does the x to the 4th and the 1/x simplify? X cubed, and then the over 4 I put in front. If you didn't, it would be over 4 inside of here. Yeah. And then dx. And you can integrate that, can't you? Sure can. All right, so we have a 1/4 x to the 4th ln x. And then I have a 1/4. What is the antiderivative of x cubed? Kind of feel like we already did that. What is it? It's x to the 4th over 4. Or 1/4 x to the 4th. And then what else do I need here? Yeah, plus c. We didn't deal with that hardly at all in Chapter 7 because we were always actually finding definite integrals, right? We had limits of integration to substitute into that. So don't forget that's part of what we're working on back here is we're back to an indefinite integral. So we're going to simplify just a touch. I have 1/4 x to the 4th natural log of x minus 1/16 x to the 4th, or x to the 4th over 16 plus c. What do you think? It's a little different, right? Okay, so let's take a look at another one. All right, our guidelines are going to be a touch more helpful on this one than they were on the last one. All right, so if it's me, I would be setting up my visual piece in this order, u, du, and v, dv. Regardless of whether you like my visual ordering, you need to have it written down somehow anyway. This is as good a way as any, I think, probably. So I fill in along the top to bottom diagonal the u and the dv, and the pieces that I have to fill in with are the x cubed and the e to the x, and you know that the dx goes down here. That's a given, okay? All right, so x cubed and e to the x. Let's talk about these. What's the benefits or the detriments of each of these? What are the nice things about them? What's the nice thing about x cubed? It simplifies if you take the derivative of it, right? And we found in the last problem that it's also another option is to have it in that dv spot because we know how to take its antiderivative as well, right? So it could actually go in either spot. Tell me something about e to the x. It's e to the x, whether you take its derivative or its antiderivative. So again, it has this nice feature that it could go in either spot, right? So unlike the last one where the natural log of x had to go down in a certain spot, it had to go into that u spot. We had no choice. Here, we have all the choice we want, which means those guidelines become helpful. So using those guidelines, which one should I put where? X cubed in the u spot. And why? Because it becomes simpler when I take the derivative of it. I mean, that's it. That's all there is to it. Now, the nice thing, of course, then about this e to the x is that when we take the antiderivative of it, it's not any harder than it was before either. That's actually kind of nice. All right, so what is the derivative of x cubed? 3x squared dx, right? And what is the antiderivative of e to the x dx? E to the x. How nice. All right, so we're going to take this one, and the first thing that I do when I'm actually doing the integral now is to multiply across the top of the pieces that I just worked through, u times v. So what will that look like? X cubed into e to the x multiplied, right? And then I'm going to subtract an integral, and what's going to be inside of my integral that I subtract? V and du. So the other diagonal. So v is e to the x. Du is 3x squared dx. I could pull the 3 out in front, and that would be fine. But I've got an inherent problem going on here. Can anybody see what my problem is? Very good, Jordan. Why in the world would I have to do the same thing again? What's going on? I still have a product, don't I? Yeah, that's not so friendly. But you know what? We can do it again. So I don't actually want to pull that 3 out in front because then I'm going to have to keep track of it all the way along. I'd rather just leave it attached to the x squared so I don't have to remember to apply it to everything. I'm already going to have to apply a negative. I don't want to remember a 3. Okay? So I'm going to have to do this again with this piece only now. Okay? So I'm going to do another one of these, u du v dv. So what should u be? 3x squared is a good choice. Why? The derivative becomes simpler. I mean, that's just all there is to it. So then what does dv become? The other piece, e to the x dx. So the only pieces that I am identifying here are within this piece right here, right? I'm not working with the x cubed or the e to the x. That's done. That part is done. I don't have to take an antiderivative of it. It is already part of the answer, and it is finished. Now, we still have to remember not forget it along the way, but we don't have to do anything with finding an antiderivative of it. It's already been done. All right, so then what is the derivative of 3x squared? 6x dx. And what is the antiderivative of e to the x dx? E to the x. All right, so as I mentioned before, I've got to keep track of some of this stuff. So I've got my equals, I've got my x cubed e to the x, none of that changed, and I've got my negative. All of those pieces still are there. But the part that comes next comes from this new piece of blue work that I did right here. So I have to multiply the u times the v, right? So I've got e to the x times the 3x squared. So I'll put the 3x squared here, and then the e to the x, and then I've got a subtraction sign and an integral. And then I use the other diagonal, which is going to give me the 6x and the e to the x. So I've got e to the x, and I have 6x dx. Now, I'm going to go ahead and distribute the negative through here, but do you see a problem? There's still a product. Like, isn't that just so frustrating? I mean, we're going to have to do it again, a third time. But it will be our last time to do it. So, okay. All right, so let's see what we have. We're going to simplify out the negatives because I don't want to keep keeping track of them. So this is actually a minus 3x squared e to the x, and then it's plus the integral of e to the x times my 6x dx. So the part that I'm going to be working on is this piece right here, right? All of this is going to stay with my next part of my problem, and I'm going to take my integral and do integration by parts with just this last piece. Let me see if I can get this to copy to my next slide. All right, so over here on the side, I'm going to deal with the beautiful integration by parts. Sorry, I can't keep saying it wrong today. Over here on the side. What is u going to be? 6x. And what is dv going to be? The same old e to the x, right? dx, you got it. Now, what is the derivative of 6x? 6. And why is that so friendly right now? There's no variable. It's just a constant, right? That's why. You got it. I do have a dx, though, so let me put that in there. Now, what's the antiderivative, then, of e to the x? E to the x, you'll never forget it because we've done it 3 times in a row. And now we're actually ready to continue with the work we were doing before. So coming down here, I still have the x cubed, the e to the x, the minus 3x squared times e to the x, plus. Now, everything after this is going to come from this new piece of blue work that I've done on this slide. So I've got a plus sign there already. So I'm going to have across the top the 6x e to the x, right? And then I'm supposed to have a subtraction. There it is. What am I going to be subtracting then? My integral of what? 6 times e to the x dx. And I can finally take that antiderivative without anything else needed, right? Yeah. All right, so I've got x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus what? 6e to the x. And it's not that I just rewrote it, it's that that's actually the antiderivative of the one I already worked with, right? So I actually take the antiderivative of the 6e to the x, and it is 6e to the x. It's going to come up soon. After I have my minus 6e to the x here, what's going to come next? Plus c. Okay, so no discussion of integration by parts would be complete if we did not discuss something with some trig in it. So that's where we're headed next, all right? At least in theory. The screen will change. There it is. Okay. Now, this is an interesting problem, all right? And the reason it's an interesting problem is because of what happens in the middle of us doing our integration by parts. So taking a look at what we've got here, you've got e to the 2x and you've got sine x. And we've got an inherent problem, which is what? Do you know? So if we put sine in wherever we put it, it's going to switch back and forth between sines and cosines. It's never going to get any simpler, right? What about the other piece? It doesn't get simpler either. The height of unhelpfulness, right? I mean, really, it is. It's the height of unhelpfulness. Neither of those are going to get any simpler, so that's not helpful. However, there is one piece that becomes messier if you take its antiderivative than if you take its derivative. Do you know which piece it is? E to the 2x. Why in the world did I say that? Why is e to the 2x easier to take a derivative of or cleaner than if I take the antiderivative of it? Because you've got a u substitution going on, right? And even if you sort of start to feel like I don't really need the u substitution, at the very least, your solution will have division in it instead of multiplication. And it just looks messier to work with division and multiplication. I mean, it just does when we look at the answer. So, because we don't have any reason to do it anything else, I mean, we don't have any other sort of a way to go, we're going to use the e to the 2x as the u. For every reason that you guys already said. And we're going to use the sine x dx as the dB. Now, just bear with me as we work through this, because it's not going to look like we're making any progress for a little while. Okay? But I promise we will. All right, so what is the derivative of e to the 2x? 2e to the 2x dx, yeah. What is the antiderivative of sine? It is negative cosine. Now, it is crucial beyond all measure that you get the signs, that is the positives or negatives, right on this problem. Because if you miss one, everything's going to fall apart weird. Okay, so please be careful as you're doing this one. Okay, so after we get all of these pieces put in, I want somebody to tell me what is next. What is the next piece I'm going to have? So who's going to volunteer for me today? Taylor, what do we got?
You're going to multiply e to the 2x times negative cosine of x.
Okay, can I put my negative in front?
Yes.
Okay, so I'm going to put the negative e to the 2x and then the cosine of x.
Do you want us to write it right next to it, or can we go?
No, you can go further down if it's helpful to you. I don't care how it's written, that's fine. But we're just about... All right, what's going to come after that, Taylor?
Minus the integral negative 2e to the 2x times sine x dx.
Okay, so the negative that's part of my subtraction and the negative that's next to the cosine are going to actually end up becoming...
Cosine.
Yeah, it's okay. So these two negatives are going to actually become positive, right? Is everybody with me on that? There's a negative as a part of the answer, and then I've got this negative right here with the cosine. So I'm going to end up, then they're going to cancel. So I'm going to have a positive 2e to the 2x cosine of x dx. Okay, does that look all right? But it doesn't really look any better, does it? So instead of having e to the 2x sine x, now I have e to the 2x cosine x. I mean, like, am I supposed to be excited about that? Not real helpful. So you might sort of be tempted at that point to say, well, that didn't get any simpler. Because I did one like the last problem we did. It actually got simpler. I mean, like, we knew we had to do it again, but it did get simpler. It looked better, at least. So at this point, you might be tempted, had I not already told you in advance that something was going to happen that was weird, to think, I did something wrong. This is not going to work. So we're going to try it again for no real good reason. Okay? Not try it again as in start over, but try it again as do another iteration of the integration by parts. I'm going to do another u dv. And I'm going to do it with this piece right here, the very end. So doing this again, I've got a u and a du and a v and a dv, and we've got to keep the pattern the same. Kind of like we did in the last problem. We can't go changing it now. I can't now say, okay, well, this time let's try the e down in the dv part. And that's not going to be helpful to me, okay? So we're going to put the u in, still the e to the 2x, but we'll put the 2 in with it because we don't want to lose the 2. Okay, so the u is going to be the 2 e to the 2x part, and the dv is going to be my cosine of x dx part. Is everybody with me still? All right, so what's the derivative of 2e to the 2x? 4e to the 2x dx. And what is the antiderivative then of cosine of x? Sine, with a positive in front of it, right? With sine x. Alrighty then. So we're going to come down here. I have the negative e to the 2x cosine x. And I've got plus. Now I'm going to do the next part of my integration by parts, right? Previously I had plus this integral. Now I've done this new piece of blue here that's got different pieces. So Taylor helped me last time. Somebody else who helps me now? Janet. Okay, so you did the u times the v, right, Janet? Okay, and then what? Times sine. Yeah, it's the second diagonal on that piece, right? Good. And once again, that doesn't look any better. Or does it? Let me show you what we've really got at this point, okay? I'm going to move this to the other slide. Okay, let's try that again. I got that left off. Okay, so I think this is where I am, right? I'm trying to find what's on the left, the integral of e to the 2x sine x. And right now what I have is what's on the right. And the problem is that what's on the right still has an integral in it. Everybody's good so far? But notice what can happen. Sorry, that's a 2 right there I left off. Okay, so all I did in that step was what? Take out the 4. That's it. I mean, nothing special. Except that something special did happen. Does anybody see it? We're actually going to add it because it's negative on the right. So in doing that, Janet, what did you notice? Why is that something you want to do? What are you noticing? Okay, so if I move the integral that's on the right side to the left side, it will combine with what's on the left because the integrals are the same, aren't they? This integral on the left is exactly the same as the integral on the right. The only difference is the 4 in front. So it's helpful to move it because it can combine with what's on the left-hand side because they're the same. Are you with me? So this is sort of an algebra thing going on in the middle of the calculus. It's kind of a weird one. We didn't have that before. But we have it now, and it is helpful. So we're going to add the 4 integral of e to the 2x sine x dx to both sides. I don't mean for those to be looking like they're division. I'm sorry about that. So in adding that, how many of those do I now have on the left? There are 5 of them, aren't there? So I have 5 times the integral of e to the 2x sine x dx equals negative e to the 2x times cosine of x plus 2e to the 2x times sine of x. And we'll go ahead and put in our plus c. It has to be there at the end anyway. We usually just tack it on at the end and don't mess with it in the middle, so I'll just put it in right here. Or you can wait till the end. Actually, that might be a little bit cleaner because I'm going to do one more thing. Well, I'll take that back. We'll do it at the very end. Okay, so my goal is not actually to solve for 5 times this quantity. It's to solve for the integral quantity, right? So what am I going to have to do with that 5? We're going to divide. So we'll divide everything, each piece of our... Now this is an equation, each piece of our equation by 5. So on the left, I have exactly what I started with. I have the integral of e to the 2x sine of x dx. And on the right-hand side, I have all the pieces I need, and then I have to put the plus c. So I have a negative, I'm going to write it with fraction form, so I've got negative 1/5 e to the 2x cosine x. You don't have to write it like this, but I am going to. And then I've got 2/5 e to the 2x sine of x, and then plus c. So the answer is this piece that's on the right. You have at least one of those in the homework when you do get the homework for this next Tuesday. So I wanted you to see an example of how it works. Any questions? All right. We have 2 examples left, and we're going to stop right here. So I'll say stop, but don't everybody move just yet, okay?